Okay, now we will study about effect of harmonic current. Okay, distribution system component and equipment particularly susceptible to harmonic current include capacitor bank, transformer, power cables, neutral conductor, electronic motor, circuit breaker, electronic relay, and metering equipment. Okay, effect of harmonic current, for example, in the presence of harmonic, especially voltage harmonic, tend to increase the electric losses on the capacitor, increasing the operating temperature. Jadi, the effect will be increasing it operating temperature. This effect increase the thermal and the electric stress to the capacitor unit. And then the electric loss can be expressed by this formula. Sigma H equal to 1 until infinite C in the bracket tangen do close bracket omega H V H square, where tangent do it is equal to omega RC, and then omega S is 2 V FH. Vs is RMS voltage of H harmonics. H is the number of harmonics. Okay, harmonic current excite parallel resonance between capacitance of power factor capacitor bank and system inductance. When this happens, very large Vs and Is can be generated, after leading to the catastrophic failure of the capacitor bank system. This we see this the visual effects of this fault, this harmonic. The heat from this failed capacitor bank completely destroy the attachment incomer for 100-volt switchboard for a very large shopping mall. There is the example. If we see there is the single line, there is PSD, variable speed drive, and then there is PCC, point common coupling. There is the transformer, there is the capacitor bank, there is the loop motor, and there is the circuit. There is the circuit where LS is the supply inductance, C capacitance of PF capacitor, R there is resistance of linear load, I H there is harmonic current. It is the circuit, equivalent circuit of this system. Okay, by neglecting R, the impedance Z seen by the current source if given by the expression Z, it is equal to J Ls omega per 1 minus Ls C omega square. From the above equation, a resonance occurs when the denominator 1 minus LSC omega square approaches zero. The corresponding frequency is called the resonance frequency of the circuit. At this frequency, the impedance is at its minimum values, resulting in considerable voltage harmonic and consequently major voltage distortion. This voltage distortion is accompanied by the circulation of harmonic current in the LS plus C circuit with A greater than the injected harmonic current. This is the work example in order to understand this uh, phenomena, this condition. We will look at this example. Okay, consider the harmonic Ritz power distribution system with peak harmonic voltage of around 20%. The fundamental 4180 volt, 300 kV capacitor bank has a reactance of 57.7 ohm at the 50 Hz fundamental frequency, and the capacitor reactance is only 11.54 ohm at the fifth harmonics. Find the total RMS current following through the capacitor bank. There is the illustration of the system. Okay, fundamental current. How we calculate the fundamental current, and first we look at the equivalent circuit. There is the equivalent circuit, and then IC1, that is the current flow into C. It is so fundamental current. It is we can calculate it by divided phase voltage per reactant C1. Okay, phase voltage is 4180 per square root 3, and then the impedance is the reactant is 57.7, and then we get the current IC1, that is 41.62 ampere, and then the current for fifth harmonics, it is IC5. IC5, it is 20%. 20% the voltage from the phase voltage per reactant C at harmonics number 5, fifth or harmonic. It is 0.2 multiple 4180 per square root 3, and then we divide it with 11.54, and then we get the current. It is equal to 41.62 ampere, and you see there is the equivalent circuit. Okay, total RMS current, it is IRMS equal to I1 square plus IH square. This I1 square at this fundamental current is for square root. The IRMS is square root 41.62 square plus 41.62 square, and then we get that 50x.86 ampere. And then if we compare with the current I1, it is IRMS, it is equal to 141.4% from the fundamental current I1. And then this the effect is could blow capacitor fuse. This current will be blow the capacitor fuse. In such case, nuisance blowing is expected, since most capacitor fuse are sized based on the 135% kVAR limit. Otherwise, capacitor units suffer overloading and heating. This show why noisome capacitor fuse blowing and or breaker tripping indicate very high harmonic distortion level in the area. And this is the another work example. A 442 microfarad 600 volt 50 hertz capacitor has losses of 20 watt when rated sinusoidal voltage is applied across its terminal. The capacitor is installed in a factory where it is simultaneously carries a fundamental current of 100 ampere, 50 hertz, and harmonic current of 80 ampere, 80 ampere, uh, 250 hertz. The total distorted current may be described by the following equation. This is I equal to 100 square root 2 sin omega t plus 80 square root 2 sin in the bracket 5 omega t plus 25 degree ampere, and then calculate the effective values and TSD of the current in the capacitor. B. The effective values or NTSD of voltage across its terminal. C. The approximate values of the losses. Okay, this is the solution. The effective values of the distorted current, it is I equal to square root 100 square plus 80 100 square 80 square, I'm sorry, 100 square plus 80 square square root from this, and then we get 120x ampere, and TSD, it is we know the harmonics current per fundamental current. The harmonic current, it is 80 ampere, and fundamental current, it is 100. It means TSDI, it is 60%. The reactance of the capacitor at 50 hertz, that is X50 equal to 1 per 2 phi FC. That is the values. If we substitute the values, and then we get X 50, that is 7.2 ohm, and then reactant at 250 hertz, that is we substitute the values, and then we get 1.4 ohm, and then fundamental voltage across the capacitor, that is we get that VF equal to I1 multiple X 50. It is I1 100, and then X50, it is 7.2, and then we get that VF fundamental voltage is 720 volt, and then harmonic voltage across the capacitor, it is we get the voltage by multiple I5 with X 250. It is I5, it is 60, and then reactant X 250, it is 1.44, and then we get voltage V5, it is 115.2 volt. and then consequently the losses at uh, 96 volt, 250 hertz, it is R. P V power, it is power loss, 250 hertz, it is equal to 20 watt multiple 250 hertz per 50 hertz multiple, it is 115.2 per 720, and then we get uh, um, 16 watt, and then the total losses is 20 watt plus 16 watt, and then equal to 36 watt is the losses. Okay, note it IEEE, there is the regulation IEEE 18 2002 state that a capacitor is designed to operate at a maximum of 135% of its reactive power per rating. In addition, it must withstand a continuous RMS over voltage over 110%, peak overload of 220%, and of per current of 180% of nameplate rating. Although the standard did not specify the limit for individual harmonic, the above percentage can be used as a basis to determine the maximum allowable harmonic level. Okay, next we look at the effect of harmonic on distribution transformer. Okay, first reduce the system capacity. All distribution system are RMS current limited. In a system powering three-phase load, for example, a 1000 kVA 480 volt transformer is rated to deliver 100 1200 ampere RMS, but the more harmonic current this transformer has to supply, the least fundamental current it can provide for a powering load. In other words, because the harmonic current does not deliver any power, it presents simply use up system capacity and reduce the number of load that can be powered. The second is overheating of the transformer. Large power transformers are prone to a loose mechanism associated with the coil known as eddy current losses. Eddy current losses increase in severity as the frequency of the current increase. Hence, the presence of the harmonic content in the current waveform will have the effect of the increasing the self-heating of the transformer. Delta Y or delta connected transformer trap zeros when current that would otherwise overheat natural conductor. The circulating current in the delta increases the RMS values of the current and produce additional heat. And then the extra heat can have a significant impact in reducing the operating life of the transformer insulation. The overheating can be avoided by either derating the transformer or by specifying the appropriate key rated transformer. Okay, overheating transformer. Transformer are affected in two ways by harmonic. First, ID current losses 10% of the normal full load current, increases the square of the harmonic number. With a nonlinear load transformer, losses would be twice as high as for an equivalent linear load, result in high temperature rise. Harmonic in natural increase 3 times. Next, we look at K factor rating. A K-rated transformer is a transformer designed to handle the extra heating effect caused by harmonic distortion. This transformer prevent insulation breakdown by uniformly distributing the stress across the transformer winding. This result in longevity of the transformer. The K factor is calculated from the harmonic spectrum of the load current by the following equation. The K factor equal to sigma has equal to 1 until infinite has square I has square per sigma has equal to 1 until infinite sigma I has square. The typical K factor that are specified are 4, 10, 13, and 20. The higher the number, the worse the harmonic load. That is, the greater the harmonic heating effect. A K factor of 1.0 indicate a linear load at no harmonic. If we get from the calculation that we get K factor equal to 1, it means the load is linear and no harmonic. Okay. This, for example, K-rated transformer application. If the load, this is the type of load. It is motor, incandescent lamp, heating element, solenoid, transformer. K factor is K factor class 1. And then it means K factor it is equal to 1. And then for welder, induction heating unit, solid state control, fluorescent lamp, high ID lamp, that is have K factor it is equal to 4. And then mixed linear and nonlinear load, UPS, telecommunication equipment, there is the load, the system that give K factor equal to the 10 atau K the 10. And then K20, there is the desktop computer, variable frequency motor drive atau VFDs, mainframe computer. Okay. This the example of device that have K factor related with its K factor. Okay, that is the example. A transformer is required to supply a nonlinear load comprised of 200 ampere of fundamental 50 hertz, the T ampere of third harmonics, 40 X ampere of fifth harmonic, and 79 ampere of seventh harmonic. Find required K factor rating of the transformer. It is I1 and the fundamental it is 200, I third it is harmonic third vector harmonic. This the T ampere, fifth harmonic 40x ampere, and seventh harmonic 79 ampere. And then key vector, that is, we have the formula for previous formula, and then we substitute the values. That is 200 square plus multiple 1. It is has 1 has equal to 1 square, and then plus 3 the T square multiple 3 square plus 40x square multiple 5 square plus 79 square multiple 7 square, and divided with 200 square plus the T square plus 40x square plus 79 square, and then we get that K rating it is x point 323. To address this harmonic loading in the example, to address the harmonic loading in this example, you should specify a transformer capable of supplying a minimum of 222.4 ampere with a K rating of 9. K rating it is 9. Okay, transformer derating. The curve present below show the typical derating required for a transformer supplying electronic load. Okay, in this example, if the transformer supplies on overall loading comprising 40% of the electronic load, it must be derated by 40%. It means if the hour load, the 40% of load it is electronic load, and must be derating 40% because of the electronic load will be produce the harmonic. Okay. Example L delta Y connected isolation transformer of 13.x per 2.3 kV is required for 2.3 kV 3000 HP drive motor connected to a load commutative inverter LCI with the following current spectrum. This is the spectrum they give. I1 693 ampere, I5 that is 121 ampere, I7 79 ampere, I11 31 ampere, I13 20 ampere, I17 11 ampere, I19 7 ampere, I20 6 ampere, I25 5 ampere. Calculate it harmonic loading. The loss data for the transformer supplied by the manufacturer, and the harmonic frequencies affecting the rating of the transformer are given in table 1 and table 2 respectively. Okay. It is the no load losses. No load losses. There is 380 3800 watt, and then I square R losses. This 20 kilowatt, and then eddy current and stray losses 3200 kilowatt. Total load losses it is 23 kilowatt. Total transformer losses it is 27 kilowatt. And then the linked flux has its maximum concentration between interface of two winding VICR. It is 16% of the I square root R losses. And then there is frequency. It is his number of harmonic, and it is the frequency in unit. 1 it is 1, the 5 it is until 25 00 point x unit. It is in unit. Solution. A transformer supplying a non-linear load may have to be derated. Harmonic effective transformer losses and eddy current losses density. The upper limit of the current distortion factor is 5% of the rated current, and the transformer should be able to withstand 5% over voltage at rated load and 10% at no load. The harmonic current in the applied voltage should not exceed this limit. In addition to it, the rating due to increased harmonic induced eddy current losses. A drive system transformer may be subjected to serve current cycling and load demand depending on the drive system. The losses in a transformer can be divided into one, there is no load losses, and then second it is load losses. The load losses consist of copper losses in the winding and stray losses. The stray load losses can be subdivided into the losses in the winding and losses in non-winding component of the transformer. For example, core, clamp, structure, and tank. The total transformer losses loss it is PLL. We can calculate it. The PLL equal to V plus PAC plus POSL. The P equal to I square root R loss. PAC it is winding eddy current losses, and POSL it is other stray losses. If the RMS values of the current including harmonic is the same as the fundamental current, I square root R losses will be maintained the same. If the RMS values due to the harmonic increase, so does the I square R losses. The RMS values of the current spectrum including the fundamental is given by the following formula. Formula number 2, it is in per unit. IPU equal to in the bracket sigma has equal to 1 until has maximum in the bracket I has PU square close bracket power half or square root. And then if we substitute the value, if we substitute the value for each of I, and then we get that IPU it is 709 ampere. And then the eddy current loss VEC is a sum to vary in proportional to the square of the electromagnetic field strength I square or F square can be considered to be representative of it. Due to this skin effect, the electromagnetic fluid may not penetrate a conductor at high frequencies. The linked fluid has it a maximum concentration between interface of the two winding. And then VEC in VU it is VEC minus R VU multiple sigma has equal to 1 until has maximum in the bracket I has PU square multiple has square, where VEC R PU is the winding eddy current losses under rated condition. All the stray losses are assumed to occur in the winding. Hence, PLL can be written as PLL PU equal to sigma has equal to 1 until has maximum in the bracket I has PU square plus PAC R PU multiple sigma has equal to 1 until has maximum I in the bracket I has PU square plus has square plus has square. This equation for then the few values of the few values of non-sinusoidal current is given by equation 5, where PU RPU is calculated from the transformer test data, and the maximum eddy current losses density is to be assumed 400% of the average value. The division of eddy current losses between winding is 60% in inner winding and 40 in outer winding for all transformer having a self-cooled rating of less than 1000 ampere, and for all transformer having turn ratio for 1 or less. And then 70% in inner winding and 30% in outer winding for all transformer have turn ratio more than 1, and having one or more winding with a maximum self-cooled rating more than 1000 ampere. Okay, PEC RPU is specified by the manufacturer or is given by PEC R equal to total loop loss minus copper loss, or we can write it PEC minus R equal to PLL minus K in the bracket I square 1 minus R multiple R1 plus I square 2 minus R2. This expression for copper loss R1 and R2 are the resistance measured at the winding terminal. For example, S1, S2, or X1, X2, and should not be confused with the winding resistance K1 for a single phase transformer and K1.5 for a three-phase transformer. As the low voltage winding is the inner winding, maximum VECR is given by this formula. Max VECR VU equal to K1 VECR in watt per K multiple I2 minus R square multiple R2 watt, where K1 is the division of eddy current losses in the inner winding, equal to 0.6 or 0.7 multiplied by the maximum eddy current losses density of 4 PU. An example, or 4 PU, i.e. 2.4 or 2.x, depending on the transformer turn ratio and current rating. Considering the RMS current as the PU base current, or the PU uh, I has are calculated as tabulated below. Corresponding other parameters to be used in their calculation are also given in this table. For has equal to 1, this is the values I has, and then I2 pi2 I has square, I has square multiple has square, f has square multiple has square. This is the value. This is the sigma. It is equal to 1. That is the values. Since VEC R VU is 16% of the I square root I square R losses, the maximum load losses density under the rated load condition, it is VLLR VU is 1.16 VU. Therefore, the total transformer load losses is given by the PLL VU equal to P plus PAC plus P plus POSL. P equal to 1, PEC 0.16 multiple 2.7514 or equal to 1.4402 PU. This means that the transformer losses while supplying the required spectrum load are no load losses. It is 3600 watt, no change. IR loss, I square R loss equal to 20,000 watt, no change. Eddy and stray losses, it is 0.442 multiple to 20,000 equal to x 140 watt is compared to the 3,200 watt for sinusoidal load. In increase of the 5,640 watt of total load. And then the permissible current with the given harmonic spectrum is I maximum VU. That is the formula. And then if we substitute the value of its parameter, and then we get that I max VU, it is equal to 0.x79. And this show the rating of 12.1% the rating for this situation. Okay, now suppose that for the same transformer the fundamental current rating is 700 9 ampere, the voltage ratio is the 10.x to 2.3 kilovolt, and the transformer is delta Y connected. The following resistance data are supplied. R1 it is 1.052 ohm, R2 it is 0.0159 ohm, and the total load losses is 23,200 watt. The primary winding voltage, it is the primary risk voltage, it is the 13.x kilovolt, and then winding current it is 71.90 ampere. The copper losses in winding is give with this formula. Copper losses are equal to K in the bracket I 1 minus R square multiple R1 plus I square 2 minus R2 multiple R2. And then if we substitute the values, and then we get that copper losses it is 19,986.3 watt. Okay, from the given losses data, VECR, that is the total load loss, itu PLL minus copper losses. It is equal to 33,200 minus 19,986.3, and then we got that VECR is 3,218.7 watt. And then the maximum PEC R max, it is V is equal to V max VEC R VU. This is the formula equal to K multiple VEC R divided to K in the bracket I2 R square multiple R 2, and then after we substitute the value, and then we get that VEC R max equal to 0.643 PU, the unit in PU. This is the effect of harmonic into the transformer. Next, we look at the effect of harmonic on the power cable. Okay, the primary effect of the harmonic current on the power cable is the additional heating due to increase in the I square root R losses. This can be attributed to the two phenomena known as the skin effect and proximity effect, both of which vary as a function of frequency as well as conductor size and spacing. Skin effect is the tendency of an alternating electric current AC to become distributed within a conductor such as that the current density is largest near the surface of the conductor and decrease with greater dips in the conductor. It has a very little effect at power system frequency, for example 950 90 Hz, but above 300 350 hertz, skin effect will be significant. That is the skin effect. It is the skin effect. You see if the frequency 6000, where the concentrate, it is the concentrate of the current, it is the concentrate of current, it is the concentrate of current. You see the effect of the concentration into the current concentration. When two or more conductor carrying AC are close to each other, the distribution of current in each conductor is affected due to the varying magnetic field of each other. The varying magnetic field produced by AC induces eddy current in the junction conductor. Due to this, when the nearby conductor carrying current in the same direction, the current is concentrated at the farthest side of the conductor. When the nearby conductor are carrying current in opposite direction to each other, the current is concentrated at the nearest part of the conductor. This effect is called a proximity effect. The proximity effect also increase with increase in the frequency. Effective resistance of the conductor is increased due to the proximity effect. Okay, the effect of the harmonic heating in the cable is normally not a matter of great concern. However, in designing and sizing, one should consider the rating the conductor in order to account such unwanted effect. Number 7, this cable involved in the system resonance may be subjected to voltage stress and corona, which can lead to the electric or insulation failure. Power cable carrying harmonic loop X to introduce EMI, electromagnetic interference, in the junction signal or control cable via conducted and radiated emission. The EMI noise has a detrimental effect on the television, radio, computer control system, and other type of equipment. Now we look at the effect of harmonic in on natural conductor. Okay, if there are significant and nonlinear load in a three-phase four-wire system, the natural conductor become overload due to the presence of the third harmonic current following through it. With a TSD defined as TSDI equal to square root in the bracket I RMS square per I1 minus 1. It may be judged that IRMS is equal to I1 square root 1 plus TSD I square. It is the work example, and there is the visual of the damage effect of the harmonic on the cable. Calculate the RMS current carried by a power cable based on a current total harmonic distortion TSDI of 42% of the fundamental current of 600 ampere. It is the solution. It is I RMS. It is equal to 100. I'm sorry, 600 multiple square root 1 plus 0.42 square. It is equal to 651 ampere. Ignoring the effect of skin and proximity effect, the IR square R losses in the cable due to harmonic current we will increase by the in the bracket 651 per 600 square multiple 100 square 100%. It is equal to 17.73%. It compared to the heating effect at the fundamental frequency. Okay, work example. This is number 1. IVG cable having a length of 75 meter has a resistance of 25.7 milliohm. When it carries a current of 100 ampere at 50 hertz, its temperature is then 700 Celsius in an ambient of 25 degree Celsius. After the installation of the an electric drive, the cable was found to carry an additional 7 harmonic current of 50 ampere. There are 350 hertz. Calculate the new losses in the cable and the approximate temperature raise. This is the type of the cable. This for 15 AVG 20 12 12 10 X 6 2 1 AVG. This is the current. The current 20, 25, 30, 40, 50, 55, 39, 125 ampere. And then the original copper losses due to the current of 100 ampere, that is equal to PF equal to IF square multiple R, and then after we substitute the value, we get that PF copper loss 257 watt. Assuming the resistance of the cable remain the same with when it carries the additional harmonic current, the losses caused by the harmonic component are PS equal to I square multiple R, and after we substitute the value, we get 64 watt, and then the new losses are 2057 plus 64 watt, and then equal to 321 watt. That is the new total losses, which is an increase of 24.9% compared to 157 watt. Consequently, the temperature rise will increase by 20%. Since the previous temperature rise was 70 to 25 it is equal to 70 minus 25. It is equal to 45 degree Celsius. The new temperature rise will about 1.25 multiple 45 degree Celsius equal to 56 degree Celsius. It follow the temperature of the cable will rise to about 25 plus 66 degree. It is equal to 61 degrees Celsius. Okay, next we look at the effect of harmonic on the induction motor. The harmonic cause increase heating and vibration in an induction motor. Harmonic create a rotating magnetic field at the speed well away from the synchronous speed, some forward and some backward. The rotor dissipates sleep energy, where the energy dissipated is equal to the sleep at a difference in the speed between the rotor span and the torque speed, time to the torque. The losses in the induction motor are primarily copper losses and iron losses. The result is that the operating temperature of the motor will rise, and in order to keep the winding temperature down, the motor should be derated due to the harmonic present. This is the illustration. This is the motor. The illustration, the visual of the motor. This is the where the movement. It is the negative square reflective harmonic. This is the negative square, and there is the positive square. Okay, there is the 50 hundreds rotational, and then the this is the impedance, the impedance rotation. The motor heating, vibration, and system losses. It is like driving with foot on foot and the gas and one of the brake. Magnetic field created by a negative square harmonic current of the fifth harmonic and 11th harmonic rotate in the opposite square and the fundamental by BYR or BYR to RYB. This is the transferring of the phase. Okay, now we look at the effect of harmonic on the circuit breaker. The terminal magnetic type circuit breaker. That is, for example, this terminal magnetic type breaker. We look at the first effect. The vast majority of the low voltage terminal magnetic type circuit breaker utilize the metal trip mechanism, which respond to the heating of effect of the RMS current. Okay, that is the illustration. That is bimetal, and then this is the trip bar, and then there is we call latch, and this we call contact close. This contact close. Okay, that is B condition, and this condition the contact is open. This is the close contact. It is the open. When the energize, the produce this mechanism, this part, it is produce the electromagnetic. Then the uh, pull this bimetal into this, and then the contact will be open. In the presence of the nonlinear load, the RMS values of the current will be higher than the linear load of the same power, and therefore unless the current trip level is adjusted accordingly, the breaker may trip permanently while carrying nonlinear current. And it is the thermal magnetic circuit breaker employ a bimetal strip to sense overload condition. Uh, the use of bimetal mechanism. Okay, zero crossing sensing type circuit breaker. This type of the circuit breaker is designed to interrupt this current at a zero crossover. On highlight distorted supplies with may contain line nothing or ringing. Spurious zero crossover may cause perimeter interruption of this type of the circuit breaker before they can operate correctly in the event of an overload or fault. And fixed sensing electronic type circuit breaker. The fixed sensing electronic type circuit breaker respond to the fixed values of fundamental current. When carrying harmonic current, this type of the breaker may not operate correctly due to the fixed values of nonlinear current being higher than for a respective linear load. This type of the breaker therefore may trip prematurely at a relative low level of the harmonic current. Okay. Next we look at the effect of the harmonic current on the fuse. Fuse rupture under overcurrent or short circuit condition is based on the heating effect of the RMS current according to the respective I square T characteristic. The higher the RMS current, the faster the fuse will operate. On nonlinear loop, the RMS current will be higher than for a similarly rated linear loop. Therefore, fuse derating may be necessary to prevent perimeter operating. In addition, fuse at harmonic frequency suffer from the skin effect and, more importantly, proximity effect, resulting in nonlinear uniform non-uniform current distribution across the fuse element, placing additional thermal stress on the device. Okay, the harmonic current effect on the relay. That is the electromechanical relay respond to the RMS values of the current. The relay are rarely susceptible to harmonic problem as the operating coil are usually low voltage. For example, it is 24 voltage, or feed via step-down transformer which attenuate the harmonic. However, where the voltage supply to the conventional control relay does not contain harmonic voltage or current, they may tend to operate more slowly and or with higher fixed up values and may experience earlier life failure due to additional heating within the coil. Solid state relay normally respond to the fixed values of input signal. Solid state relay may be stressed when subject to the high level of harmonic distortion and or line notching, thus reducing reliability. It is a problem caused by distorted system voltage. It is the illustration. This is the transformer, this is the VCC, this is the breaker, and then this is the speed drive, variable speed drive motor. It is the pump. Is a object load, and we look at this single line. This, if we see in the transformer or utility, it is voltage. It is purely sinusoidal. And on the PCC, you see the voltage is corrupted because of include current harmonic, and although on the loop current also uh, affect by the harmonic. It is the waveform. It is not sinusoidal. When an electrical load is supplied with the distorted voltage, then it receives harmonic voltage in addition to the fundamental frequency voltage. If a load is supplied with a harmonic voltage, then it will also draw harmonic current for its frequency of applied voltage. The major problem with voltage distortion is a load supplied by a distorted voltage source may not operate properly or efficiently. Voltage distortion has minimal effect on a distribution system, but unlike current distribution, it is not phase dependent. So harmonic voltage generated in a part of a facility will appear on a common basis within the facility. For example, the presence of the high voltage distortion at the terminal of the nonlinear loop doesn't mean high distortion will be present throughout the system. In fact, the voltage distortion become lower the closer a bus is located to the serve transformer. However, if the excessive voltage distortion does exist at the transformer, it can pass through the unit and appear in the facilities distant from the origin. Yeah, this is the illustration. Utility voltage waveform. There is the sinusoidal, and there is the VCC, power command, command coupling, point command coupling, and then you see yeah, in PSD in linear load, the waveform that is contained by harmonic or corrupted. It is the conclusion. The presence of harmonic current can lead to some special problem both on the supply and within the distribution system. Power line harmonic are created when the nonlinear load drawn non-sinusoidal current from a sinusoidal voltage source. The harmonic current drawn can result in natural current that exceeded the individual phase current. In a four-wire three-phase system with non-linear load, harmonic current can lead to a large current in the natural conductor, which may easily exceed the conductor NMS current rating.